Hi everyone, today I'll be presenting a project developed at BrainHack 2024 in Toronto, made by myself and 6 other collaborators. Our project focuses on 2 key objectives. First, building a machine learning model to classify EEG data, and second, generating synthetic EEG data that can be accurately classified by the model. This work addresses a common challenge in healthcare data, where limited datasets often hinder reliable model training. We aim to explore whether synthetic data can effectively serve as a proxy for real data in these scenarios. Our project was divided up into several phases. Number 1 was data collection. This is where my teammates and I used a Muse headset to record our brainwave data for 1-minute sessions each. Each person did 2 1-minute sessions, one where they only focused on their breathing and one where they thought of faces. Thus, there will be 2 classes for our model, rest and faces. After data collection, we filtered our data. This involved removing unnecessary noise in our dataset, isolating specific brainwaves, normalizing our data, and aggregating frequency bands into a summary signal. Then, using the filtered data, we trained a random forest model to distinguish between the 2 classes, rest and faces. We also intentionally left out one dataset from the training data so that it can be later used to test our model on unseen data. Next, we fed our training data into a generative adversarial network, or GAN, enabling it to generate new synthetic data based on the patterns it learned during training. Finally, we tested the previously trained model on the synthetic data generated by the GAN to evaluate its ability to accurately classify the data into the 2 classes. This was a brief summary of our workflow, but there is more information regarding the different tools and steps used in the description. Now, I'm just going to present a run-through of the project, but before I hit start, the real collected EEG data is in these 2 folders over here, one for testing and one for training, and the synthetic data generated by the GAN is over here. This is what the real data looks like, and this is what the synthetic data looks like. Also note that we already have the synthetic data present because the GAN has already been trained and the data was outputted, but the code to do so is in this file here. Now, let's run the program. So, after some time, the program has filtered our data, built a random forest model, and trained on our data, and then the model has been tested on a set of unseen real data and a set of unseen synthetic data. To start, here are some visualizations produced to highlight the filtering of our EEG data. I'll first go through the time domain signal plots. There are 4 different outputs for each of the 4 channels. The plot on top represents the original data signals, and the bottom plot indicates the clean signals for each channel, highlighting the removal of noise. Additionally, the frequency band plots show different brainwave ranges for analyzing patterns of brain activity. Now, after filtering, we trained our model, which received a training accuracy score of around 90%. Along with other metrics included here, including a confusion matrix. After training, we tested an unseen real dataset on our model, and it received around a 95% testing accuracy, along with some other metrics shown here. Also, after training, we outputted a visualization of our AUC-ROC curve, as shown here, which achieved a score of 97%, indicating excellent model performance in distinguishing between classes. Also, we outputted a learning curve of the model's performance on the data as training examples increase. Finally, although we achieved an excellent score for testing with real data, the model performed poorly when fed synthetic data, as shown here. The reason for this may be due to differences in the distribution or quality of synthetic data compared to real data, or the model may have overfitted to the real data, potentially due to our limited dataset including EEG data of only a few people. This overfitting may have made our model less adaptable to variations in synthetic data that do not align with the training dataset. Overall, our model was able to classify real-world EEG data into distinct categories, but when fed synthetic data, it performed poorly. Although we believe that synthetic data can still be valuable for healthcare when it is generated optimally using larger and more diverse datasets. This is because it preserves patient privacy, supplements limited or imbalanced datasets to improve model performance, and provides a cost-effective, scalable solution for experimentation and testing. Thank you for listening.